Hello everyone. Today we are here to present one of the workshop paper, which is the title of the paper is optimizing CDN architecture with multimetric algorithm breakthroughs for edge and distributed performance. I am MD Noor from Graduate Center CUNY. Today we will discuss about some of the overviews of the CDN, the inherent challenges to address for CDN, our goals and contribution for the problem, the problem formulation and system model, the outline of the algorithm we picked to make sure to efficient our system, some of our experimental setups with the results, and the conclusion and future scope of the project. CDN is designed to deliver content efficiently across global locations. They accelerate content delivery for applications like video streaming and IoT. It has a significant impact in digital ages. Some of the usable trends are majority of internet traffic, particularly for media delivery. Some of the challenges we are facing is the scalability, performance, efficiency, and adaptability. The goal of this research is to make sure that we are enhancing the CDN scalability to meet increasing global demands and improve the efficiency and performance of CDN architecture. The key contribution of this paper is to develop a dynamic algorithm for adaptive server selection. Introduction of multimetric analysis. This multimetric approach is suitable for assess performance across multiple variables, such as RTT and CPU utilization. Experimental validation in both testbeds and HLI configuration to demonstrate scalability and performance enhancement. How to effectively scale CDN architecture to manage increased loads without compromising on performance? Well, to answer this question, we tried to implement dynamic algorithms. For this project, there are 4 dynamic algorithms for real-life server selection based on current network conditions and user demands. Another problem formulation question was, what sort of strategies that can be applied to optimize resource utilization while maintaining or improving server quality across distributed networks? To address this question, we developed a multimetric analysis framework that considers various performance indicators to make sure optimal CDN operation. For the system model, we consider 2 different system models. One is large-scale distributed system, which replicate the real-life scenarios, where the CDN servers has different nodes across the globe, which emulates high-end computation and scalability, which we implemented in Fabric testbed, which is a recently very popular testbed. The predecessor of Fabric was Chameleon and Genie. This setup is designed to replicate large network environment and measure performance at scale. We use another configuration, which is edge-like system. For that configuration, that represents smaller CDN setups with minimal system requirements. This sort of configuration actually implemented for any of the IoT devices and the handy devices we're using. This configuration is used to test CDS performance under controlled and constrained resource conditions. Here you can see the images of 2 of the configuration. In Fabric, the user is using the gateway server to the dedicated server to getting the content. On the other hand, for local edge configuration, the user and 2 server. On the other hand, for the scalability in Fabric, we use 4 server just to replicate the real world scenario. These are some of the details of our experimental setup. In testbed configuration, which we implemented in Fabric testbed, it utilized the large and distributed network to evaluate the scalability and performance of CDN algorithms. This testbed configuration also involved multiple server nodes configured across various geographic locations to mimic real-life traffic and user patterns. On the other hand, for local edge system, we emulate the smaller resource-constrained CDN environment to test the performance and efficiency on CDN algorithms like limited conditions. Also, across the globe, the internet traffic is very different based on the geolocation the consumer are there. So two different configuration meet that heterogeneity. So now we'll discuss about the algorithms which we optimized to make sure that we are ensuring the CDN performance better than before. The first one, the goal is to streaming the dash videos with HTTP directs. Here what's happening, it's like a dash player which intercepts the HTTP request, process media segments, construct it, and updates direct URL and log details. The impact of this algorithm is optimizing media delivery and reduces buffering by ensuring that media segments are efficiently redirected and handled. Second algorithm is for MPD file processing with throttle downloads. The purpose of this algorithm to process MPD file to retrieve video metadata and manage media segment downloads under network throttling, which is pretty common in internet traffic. Here, this algorithm retrieves the video ID and segment count from an MPD file, then downloads the segment while implementing throttling to simulate network condition, which is a parallel process. The impact of this algorithm is to ensurement of consistent video playback quality under varying network conditions by managing download speeds because it's a parallel process. The third algorithm is server selection based on ping. The purpose of this algorithm is to minimize latency by selecting the server with the lowest round trip time to handle client request. The operation of this algorithm is ping a list of server, measure their RTTs, and choose the server with the lowest RTT. Uses a random server as a fallback if no valid RTT is found. This operation is also one of the proof that single point failure can be avoided. The impact of this algorithm is to improve the user experience by reducing latency through optimal server selection based on real-life network performance. The fourth algorithm is dynamic network delay modification with traffic control. The purpose of this algorithm is to test the robustness of CDN under various network delay conditions to mimic the real-life scenarios. In this algorithm, we are generating random delays between 200 to 800 milliseconds. We are fluctuating these to mimic as close possible to the real world to monitor and adjust based on the Poisson distribution. The impact of this algorithm is to assess CDN performance and resilience under stimulate adverse network, helping to understand and improve CDN behavior under stress. Now we'll discuss about the hardware specification of our fabric testbed, which is mimicking the distributed network across the globe. So we're using 4 cores, 8 cores, and 8 cores respectively, where the RAM is 8, 16, and 2. So we are using different configuration because the heterogeneity of devices and network can shows different results for the CDN. So we are trying to mimic that. That's some of the configuration setup. Here we can see that's the fabric net from the client, and using the gateway server, we are connecting with 4 servers. And since we are started with 4 and then we scale it to 8 and then 12 eventually to ensure the scalability of our approach. So now we'll discuss about the results we are getting. In terms of performance and scalability analysis, we use two different metrics. One is RTT and CPU utilization. Previously, some of these autos, they actually use RTT, which is round trip time. But we saw that using just one single metrics could be misleading sometimes. So we tried to do it with the different, or we could say two different matrices. One is RTT and another one is CPU utilization. And we use two different test environment as well to mimic the real life world. One is for the region based, which is for fabric testbed, and another one is constrained edge systems for the mobile devices. So our key finding is that notable RTD reduction in the fabric testbed using dynamic server selection. And also edge variability. It increases the RTT fluctuation under stress in edge system, highlighting limits. We also get results for the CPU utilization. The general stability of CPU load was stable, showing effective resource management. Some of the spike noted can be observed, especially in setups because of their computational constraint. In terms of scalability and efficiency, the test-bed scalability, proven scalability with consistent performance under increased loads. And for the edge limitation, the edge system showed scalability under some of the issues under stress, pointing out that cost performance trade-offs are there. Here, some of the plots of our analysis. We can see how fabric testbeds, which mimicking the distributed system, performing way better than the edge devices CDN. And now, after using two different metrics, previously which was a single one for current sorters, RTT could be misleading sometimes because network traffic can change based on the geographical location. So rather than using only RTT, it's not sufficient enough. So we also use the CPU utilization distribution. And in both of the cases, for both of the multimetric approach, we can see that distributed CDN system has a better result with the trade-off of cost. On the other hand, edge setups for handy devices need to be optimized more to achieve such sort of results. Here, the time series of the discussion that we are having, we can see that near to the mean CPU utilization, how more CPU stability for 12 setups. On the other hand, for 4 and 8, it is way more fluctuating. The conclusion is that enhanced CDN scalability and efficiency through dynamic algorithm and multimetric analysis can show that the trade-off in server capacity expansion, and we need to emphasize the need of complex metric evaluation. Our future idea to extend our approach is to using more matrices such as bandwidth and memory for deeper analysis to see how the entire traffic and geological position can change the CDN results. Currently, we are trying to do the server selection with reinforcement learning for smarter CDN management rather than the current way of CDN server management. And we are aiming to build a CDN that are robust and efficient and responsive to real world demands. Thank you all for your patience. Good day.